operations. In this video we'll be starting from some very basic concepts, in fact probably the most primitive concepts, and we'll be working up through this series of videos to define the complex number system and various sub systems along the way and some of the most basic operations. So we're going to actually have 4 videos in this little series. They all come from one PowerPoint presentation, so you'll have one handout for the entire series of 4 videos. Video 1, this video, is going to start with primitive number concepts, then talk about natural numbers and whole numbers. Then we'll talk about the basic idea of addition, subtraction, and we'll see how that leads us to the set of integers, and we'll talk a little bit about absolute value as well. In video 2, we will look at how we can think of repeated addition as multiplication. That leads us to the distributive property, and when we try to reverse multiplication, leads us to the idea of division, which in turn leads us to the concept of the set of rational numbers. In video 3, we'll talk about doing repeated multiplication, which is exponents or powers, and when we reverse those we get radicals or roots. This is going to lead us to not only the system of real numbers, but also the even larger system of complex numbers. And we'll kind of finish up with some order of operations. And finally, in video 4, we'll kind of summarize a lot of what we've done here, and I've got a couple of good graphics that will kind of pull us all together. So once again, in this particular one, we're going to start with primitive number concepts, see how that leads us to the idea of natural numbers, and then the slightly larger system of whole numbers, the basic operation of addition, reverse that to find the operation of subtraction, which leads us to the idea of integers. We have to expand the number system to get that, and absolute value is going to be introduced a little bit as well. So if we start at the very beginning, probably the most primitive concept of number is the idea that two things will have the same amount. Today we might use the term a one-to-one correspondence. Of course, they probably wouldn't have used that term back in the prehistoric days, but this idea that two things had the same number, for example, that you have the same number of fingers on both hands, that you can match them up one-to-one. And of course, what we're doing here is we're trying to figure out how many fingers do we have, how many objects do we have. And so the primitive cultures, they started with some counting words and concepts that they had words for. And the most primitive idea of numbers basically is that we have words for 1, 2, and many. And I had one of my professors told me that there's a tribe in South America that still, this is their concept of number, 1, 2, and many. He thought he would quit his job maybe and go down there and teach number theory. I mean, how hard could it be if all they have is 1, 2, and many? Well, pretty soon you can extend this idea to the idea of natural numbers, things that we would call now in English 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. And so we have words and symbols for these numbers. Now, let's talk about a numeral versus a number versus a word. The word for is a word that stands for a concept. The numeral 4 is a symbol that represents that number. The number 4 is a concept that answers how many. So let's talk about some primitive numerations concepts. How do we represent a number? Well, one of the most basic ways is with tally marks. So here we have 1 mark per item. So here we might have a certain number of marks, and we can count these with our number system now, 1, 2, 3, 4, 5, 6, 7. But the idea is that we have a mark for every object. Now this is a level of abstraction because this might be marks on a piece of leather or something like that, or on a tablet, or nowadays maybe on a piece of paper. And that each mark may represent something larger, like how many goats you have. And it's a lot easier to carry around a little piece of paper or a piece of leather that has 7 marks on it than it is to carry around the 7 goats. So it is a little bit of an abstraction, but not too much, because there's 1 mark for every object, in this case every goat or whatever. Now, it's a little more advanced. The way we usually do tally marks these days is we sort of group them in 5. So when we put 1, 2, 3, 4 vertical lines, in the 5th vertical line we don't do it vertically, we do it at an angle like that. And then we go, our 6th and 7th one are vertical. Now this makes it a little bit easier for us to see because we're grouping in some grouping. Probably 5s because we have 5 fingers on one hand. But numerals in any system are really based on some system of grouping. Okay? The advantage of tally marks is that it accurately represents the number. And the disadvantage, though, as you can see pretty easily, is that this becomes very cumbersome for large numbers. How would you like to write the tally marks, even with the groupings by 5, of some number like 357? That would be rather cumbersome. So we need a better system. Well, some of the ancient cultures, such as the Egyptians and the Romans, introduced symbols that stood for groups. The Egyptians had symbol for 10, another symbol for 100, symbol for 1,000. The Romans had groups actually grouped in 5s and 10s. So an eye was a single item. So 5 eyes is a V. So the symbol V represents 5 items. 10 items, 10 eyes is represented by an X, and so forth, and they have more. Now this is an additive system, so when you see XI, it means X plus I. It means 10 plus 1 is 11. In the most primitive form, this is all they had. In the Middle Ages, they added a subtractive property and a multiplicative property, but that was much later. The most primitive numbers, they just simply had an additive notation. So if you ever get enough of the smaller symbols together, it can be replaced by a larger symbol. Now the advantage this has over tally marks is that symbols for grouping makes for a more compact representation. But they have a really big disadvantage compared to our number system, and that is that they cannot represent arbitrarily large numbers without excessive symbol repetition. At some point, they run out of symbols to represent the numbers. And then from there on, you have to repeat symbols just like you do with the tally marks. Now this problem was first really solved by the ancient Babylonians. This would be in modern day Iraq. The Babylonians at that time had probably the most advanced culture in the world at that time. And they had the world's first use of what we call place value. Now their place value is a little different than ours in the sense that it used a base of 60, whereas we use a base of 10 today. So the idea is one group of 60 is represented by 1 in the second place value. And 60 of the second place value was represented as 1 in the third place value. And 60 of those were 1 in the next value, and so forth. And so the advantage this gives us is that a few symbols could represent arbitrarily large numbers. Now, by the way, we still have holdovers from this ancient Babylonian numerals, particularly the base 60 numerals. And here are a couple examples. You probably could have thought of these. 60 seconds is 1 minute, and 60 minutes is 1 hour. This idea that we divide an hour up into 60 equal parts and a minute called a minute, and each minute is divided up into 60 equal parts called a second, that comes straight from the ancient Babylonian days. We do the same thing for angles. 1 degree is divided up into 60 parts. They're also called minutes. And each 1 minute is divided up into 60 parts, which is called a second. So you also have seconds and minutes for both time and angles. But that's an example of where we're still using this old Babylonian base 60 grouping. Now our number system is called the Hindu-Arabic numerals. It's a little bit more modern than the Romans or the Babylonians. And it uses a place value as well, a base 10 place value. Why do you think you use a base 10? Well, probably because we have 10 fingers. And the Hindus in India combine this to start this out. It's called Hindu-Arabic numerals because of its history. The Hindus in India were the first ones to come up with this, and they took a couple ideas. They took the base 10 idea of grouping in tens that maybe the Egyptians and Romans had used, but they also combined that with the place value idea that the Babylonians have. Now, I don't know enough about the history of this to know for sure, but I suspect that they at least got this idea of place value from the Babylonians, who were around had the place value much earlier. They were also one of the primitive cultures to first use a symbol that we would call 0 to represent two things. First of all, the absence of items. You just didn't have any items. That's 0 items. And also to use as a placeholder for bigger numbers. Now, this was transferred from India by contact with the Arabic Muslim Empire in the Middle East, and then eventually it made its way to the European Christian culture in the Middle Ages. And you can look at this diagram here pulled from Encyclopedia Britannica that shows sort of the evolution of some of the symbols that we use. So here's 1st century of the Common Era. You'll see symbols here. And notice their symbol for 1, 2, and 3 actually are a lot like, they're just tally marks that are going horizontally. And then here's a symbol for 4, 5, 6, 7, 8, and 9. Okay? By the time the 9th century had come around, they'd added this symbol for 0, and these symbols have morphed a little bit and changed. They'd started to become connected up. But you can kind of see how they have remnants of the earlier system. And then by the time we got to the 11th century, there's sort of variants of it. The Sanskrit in India has this group here on the right. The middle one is the East Arabic version, and the Western Arabic that made its way to Europe looks like these symbols here. Starting to look pretty recognizable there in the West Arabic. And by the time we get to the 15th century, we see some symbols here. And by the time we get to the 16th century, they pretty much have the same shape that we would recognize today. Okay, so somewhere in the 15th or 16th century here is when it finally made its way into Europe. Very late in history, if you kind of think about it. So up until that time, the Europeans were using Roman numerals and maybe some other forms like maybe Greek numerals. They were using those things instead of using our modern number system. So it actually is a fairly recent number system. So we have only 10 symbols. Here they are in a particular font. I think it's a Times New Roman font on the computer. Of course, we would call these symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And they can be used to represent arbitrarily large numbers. So if we have 9 objects and we add one more, they can be all put together in an arrangement like this that I'm going to call a long, or called a rod or a long. It's a 1 by 10 or 10 by 1 rectangle if we turn it. And so that makes a grouping of 10. 10 tens makes a square arrangement like this that I'm going to call a flat, which is a group of 10 tens or 100 single items. And so now when you see something, for example, this symbol 9 right here, over here on this first example, it represents actually this many objects, just 9 objects. But over here, the 9, when you see it represented here on the representation on the right, represents 9 groups of 10. So the value of that 9 is much bigger here. It's not 9, it's really 90. Whereas this 9 over here is 9 individuals. Over here it's 9 longs, or 9 groups of 10, or 90. So notice that the value of this symbol depends on its place in the number, hence the term place value. And if we continue that on out, we can take 10 flats and stack them up into a cubic relationship, and we have a big cube that's 10 flats, or 10 groups of 100, 100 tens, or 1,000 ones. So if we take a bunch of numbers like this, so here we have a bunch of blocks. Really, when we write them in our numeration system, what we're really doing is we're just grouping them in groups of 10. And so if we look at these, if you would count these or group these, you could take these individual blocks, if you actually had them laying out there, you could stack them up and you would get a group of 10, another group of 10, and you'd have 4 blocks left over. So this would be 2, 4, or 24. 20 means 2 tens and 4 more, so 24. So if you see a number like 2385, that's 2,385. Start at the right-hand side. Those are our units, 5 individual blocks. 8 is 8 groups of 10 here, 8 longs. The 3 is 3 groups of 100 or 3 flats. And the 2 here is 2 groups of 1,000, 2 of these big cubes. And so with this idea now, we can represent arbitrarily large numbers pretty simply with just a few symbols. This is a very, very cool thing. Maybe one of the nicest things about the development of numbers is the fact that we were able to come up with this this system, and we owe that to really to the Hindus, and then to the Arabs for bringing that over to Europe, and then eventually this spread to the whole rest of the world. Pretty much everybody uses these numerals these days. So, the most primitive types of numbers are called the natural numbers. These are the counting numbers. They answer the question, how many? In Hindu-Arabic numerals, they're like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and it goes on forever to the right, but it has a lowest number. So the lowest number that's a natural number is 1, but there is no highest number. The symbol for this is a N in this particular kind of a font right here, sometimes called blackboard boldface or open face font. If you're to write it by hand, it's like this symbol here. You go up and down diagonally, then you come down diagonally, and then back up straight. And so that makes the symbol for natural numbers. Graphically, you can represent these as dots. Starts at 1 on the left, and then we go 2, 3, 4, 5, and space these out evenly in a straight line, and they go forever to the right. That's what this little arrow is indicating. But they don't go forever to the left, and there's not stuff in between. These are the natural numbers. Now, ultimately, most ancient cultures and even primitive cultures eventually got to the point where they developed the set of natural numbers. They maybe used different symbols for them, different numerals. They may have used different grouping. They may have used place value. Maybe they didn't. But they had this concept of a natural number. Okay? But not all ancient cultures had a 0. We saw that the Hindus did. The Mayans in the New World also had, in the Western Hemisphere, had that as well. But this 0, if we throw that in with the natural numbers, that makes the set a whole number. So we got a little boldface W there. And so notice that the natural numbers are a subset of the whole numbers. We'll talk more about sets and unions and intersections and subsets in our second unit of this course, but we can illustrate this symbolically as saying the set of natural numbers is a subset of the set of whole numbers. That means every natural number is a whole number. The whole numbers might include some other things. In fact, it includes just the point 0. But the natural numbers union the set 0 makes the set of whole numbers. And so notice our representation is so same as our integers, or same as our natural numbers, but we also have one more to the left, 0. So here are a couple exercises, a few exercises here for us to do. We're going to see if you can do these. The standard numerals we use are called what and why. List all the whole numbers that are not natural numbers, all the natural numbers that are not whole numbers, and so forth. Well, I'll let you read this on your own for the rest of this. And what we're going to be doing in many of these videos is I'll be asking you to pause the video and work some exercises before you go on. So in just a second, I'm going to say press pause now, and then you're going to press pause on your player. You're going to work these problems, write down the answers, and then press play again when you're finished, and we'll check these. Okay? So go ahead and work these. Press pause now. Okay, well, you're back. Let's take a look at the answers to some of these questions. The standard numerals we use these days are called Hindu-Arabic numerals. Why are they called this? Well, it's because of their origin with the ancient Hindus and their subsequent modification and use by the Arabs before being adopted by Europe and ultimately the rest of the world. List all whole numbers that are not natural numbers. Well, the only whole number that's not a natural number is the number 0. List all natural numbers that are not whole numbers. Well, that's impossible. There aren't any. All natural numbers are whole numbers. What feature of our number system allows us to write arbitrarily large numbers with only a few symbols? Place value does this. The idea that we group in some group, in our case in the base of 10, so group in tens. And then we group 10 tens, and 10 of those, and 10 of those, 10 of those. And we just keep grouping in higher and higher groupings of 10. So what is the base of our number system? Well, it's 10. It's this many. You can see the marks there, so you can see what 10 really means. And that's our base of our system. Why do you think that base was chosen? Well, probably because we have 10 fingers. And fingers are, pardon the pun, handy to count with. Okay? And so ancient cultures would have chosen that, perhaps, to do that. What's the smallest natural number? 1 is the smallest natural number. What's the smallest whole number? 0. What's the largest natural number? Well, there is no such thing. The set of natural numbers goes on forever to the right on a number line. So there is no biggest or largest natural number. They increase forever without bound as we keep going. This funny looking N stands for the set of natural numbers, and the one for W stands for the set of whole numbers. So now that we have our set of natural numbers and even whole numbers, we might want to do some basic operations with them. And one of the most basic operation is addition. And really, when you think about addition, all we're really doing is just putting stuff together and counting. So if you have two quantities of objects, like we have a blue number, with some blue blocks and some green blocks, we just want to add, we have 4 blue blocks, 8 green blocks. We want to find out how many we have all together. What we're really doing is just throwing all these objects together and seeing what number we have. Now, of course, when we count, we might have to regroup and snap some numbers together, snap some blocks together in groups of 10. So in this case, we can take our 8 green blocks, put 2 of the blues with it. That makes a group of 10, and then we have 2 more. We can also illustrate that on a number line as you see below. We can start at the origin, which is 0. We start with our 4 blocks, which is we go to the right floor, and then from there we go 8 more to the right, and we come up at 12. Another way you can think of this is with a counting on method. So we start with 4, we'll start with 0 and count up 1, 2, 3, 4, and then start with that 4 there, and then count on with that. 5, 6, 7, 8, 9, 10, 11, 12, which is essentially the same as what we're seeing here. So actually, this is the wrong word here. If we're going to use this terminology. If A plus B equals C, then A and B are called the add-ins, and C is called the sum. So A and B are add-ins. I'll change that on the PowerPoint. And C is called the sum of the two. Just some terminology. So one of the first properties we're going to notice is the commutative property of addition. So notice we did 4 plus 8 already. We can also do 8 plus 4. So 4 plus 8, or start with the 8 and then add 4 more, gets you the same place. Now they are really two different operations when you think of them as a number line here, because 4 plus 8 says you start at the origin, go to the right 4, and then from there go 8 more to the right, and we end up at 12. Or we're just adding these two lengths together for a total length of 12. 8 plus 4 is different. We start at 0, go 8 to the right, and then add 4 more after that. But of course, you can really see it in the blocks method. It really doesn't matter which order we do this. We get the same answer. Now, when we say 4 plus 8 equals 8 plus 4, we've done a very specific example of arithmetic. But it's not just that 4 plus 8 equals 8 plus 4. The point is, we take any two numbers and add them in either order we want, we always get the same thing. So we can generalize that and say A plus B equals B plus A for any, say, whole numbers A and B. And now notice what we've done. When we introduce a variable, now we have gone to algebra. Which, by the way, the word algebra is an Arabic word. It came along with the Hindu Arabic numerals when it made its way to Europe. So algebra is actually an Arabic term. Now, it turns out that we can generalize arithmetic, and that is what algebra is. So in one sense, algebra just is arithmetic, but generalized. Or in another sense, arithmetic is part of algebra. So when we can say, in general, a plus b equals b plus a, that's an important algebra fact. And this is an algebra fact from probably first grade here, because this is something you've known a long time. And of course, for a first grader, this does make a big difference, because one of the models that we might use is a counting on model. So instead of starting at the origin and then counting up the first 4, we could just start with the 4 and then count on like this. 4, 5, 6, 7, 8, 9, 10, 11, 12. Or we can start with the 8 and go 9, 10, 11, 12. Well, which is easier? Well, notice that 8 plus 4 is much easier than 4 plus 8 if we're thinking of it as a counting on model. Okay, so that's why the commutative property is a pretty big deal. Now, we also can develop an algorithm for addition of multi-digit natural numbers. So, I mean, one way we could do it if we had the blocks here out was to take 23, break all the blocks into single blocks, and 41 single blocks, and then try to count up how many, put them all together, see how many we have, regrouping in tens. But we don't have to break them apart and put them back together, because they're already grouped in tens. So 23 plus 41, you can see illustrated here with these pictures. These rods here are groups of 10 blocks. And notice we can just add the single units. 3 plus 1 is 4 single units. And then we can add the 2 and the 4 tens, which makes 6 tens. So we can break the tens and the units apart and add them separately. Now, occasionally we have to do something where we have to regroup, okay? And sometimes this algorithm requires that we regroup this, okay, where it has 10 or more items in a place value. So let me do 46 plus 78. And I'm actually going to slip out of this PowerPoint here, and I'm going to go to a website here called the National Library of Virtual Manipulatives, and it's going to illustrate something that we're doing here. I'm just going to search for it. National Library of Virtual Manipulatives, and it should be the first hit. Okay, once we go down here, there it is right there. Okay, and we can look at certain operations, and this is a lower level. I think it's going to be certainly in grades 3 to 5, number and operations. I can click right there. And we have some different things that we can do here. And I'm going to go to this one here, base block addition. It will actually do this in various bases besides base 10, but we're going to just do this particular problem that we were just looking at. Now I've forgotten what my problem was, let me go back to my PowerPoint. 46 plus 78. Okay. So if we go here, we can create a problem, and 46 means 4 groups of 10 and 6 ones. Okay, and then we want to add to that 78. Okay, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. There's 78. Okay, let's see if we get the other number back again. 46. 1, 2, 3, 4. That's good. and then 6. 1, 2, 3, 4, 5, 6. Okay, so that should be 46 plus 78, and I'm going to click on Begin Problem. So how am I going to add these? Well, I need to add these together, but the problem is I get more than a group of 10. I get more than 10, or a group of more than 9. So if I look down here, I already have 8. I just need 2 more to put with that. And if I put those together, they make another long. And what do I do with that? I bring that over, I regroup and carry it over to here. Now how many singles are left? Ultimately I have just 4 singles. Okay. Now what do I have? Well, I've got these 7 longs that I had here, plus the one I moved over that was made up of singles. So that's 8. I need 2 more, 9, 10. So if I take these together, that should make a flat. And now we can see that when it's all said and done, what do we have? We have 100, 2 10s, and 4 1s. That's 124. And so you can really see what's going on with the algorithm from this. Okay, I'll be sure that you have a link to this site so you can experiment with this. It's kind of fun to play around with these and see what's going on and illustrate this. Okay, I know you guys already know how to do addition. This is just a quick review, but you know, you might have some kids that you need to explain this to, and that could be very useful. So here's some basic exercises about addition. Okay, so I'll let you read these and see if you can work these out. Go ahead and do these. Press pause now. Okay, now that you're back, let's take a few minutes to just check these answers. So what does it mean to add 2 natural numbers using a blocks model to explain? Well, if you have 2 numbers each representing a quantity of blocks, then adding the 2 numbers is the same as just putting all the blocks together and counting the total number of blocks in the combined group. So adding and counting really are kind of the same because you're just throwing them all together. Now we could have real-world applications. Here's a real simple one. John has 3 apples and Betty has 5 apples. They put all their apples together in a previously empty basket. How many apples are in the basket? Well, the answer is 3 plus 5 is 8, so there are 8 apples in the basket. Notice that when you have a real-world problem, you have some kind of scenario, something that happens. Then you have to have a question, and then the answer in this case involved the operation of addition. Sometimes you can have a scenario and ask different questions about that are not, maybe only one of those would be addition. Okay, state the commutative property of addition. A plus B equals B plus A for any natural numbers A and B. So the order you write these doesn't matter. How is the property above, the commutative property, useful in addition when accounting on algorithm? It's easier to count on starting with the larger number. So if we're given the problem 2 plus 98, the first thing we're going to do is change it into 98 plus 2, because now we can just go 98, 99, 100. Much easier than starting with 2 and then going 3, 4, 5, 6, and so forth all the way up to 100. Perform the following addition. 123 plus 745. Well, that's 868. What fact makes this problem easier? And the answer is we can simply add the like place value numbers since they are already grouped. We can add the 5 and 3 singles to get 8 singles, the 4 and the 2 tens or longs to get 6 longs of 10, and the 1 and the 7 flats of 100 to get 8 hundreds. Perform the addition 147 plus 385. Well, that's 532. What additional skill is involved here compared to the previous exercise? Well, still we're adding like size objects, but we have to do some regrouping. 5 plus 7 is 1 10 and 2 left over. So we put the 2 left over down. We've got an extra 10. That 1 10 and the 8 tens makes 9 tens. One more of the 10s out of the 4 makes a group of 100, leaving 3 tens. And that we have a total of 3 plus 1 plus 1 is 5 hundreds. Now, I know this is all elementary school stuff for you, but just trying to get us to get starting really from the basics, and we're going to build up from there. One other algebraic property that we have is a special property of the number 0. One property that 0 has is it's the additive identity, or the identity element for addition. So a number retains its identity when 0 is added to it, or 0, you add it to 0 or add 0 to it. So a plus 0 or 0 plus a is a. For example, by the way, e.g. stands for example. 3 plus 0 equals 3, and 0 plus 7 equals 7. Makes pretty much sense if you're thinking of it just as a group model of a blocks model. You start with 3 blocks. If you don't add anything to it, you still got 3 blocks. If you start with no blocks and you add 7, you have 7 blocks. It makes sense. If you think of it as a number line model, it also makes sense. 3 is no motion. 0 is no motion. So if we start at 3 and then go nowhere, we're still at 3. Or if we start at the origin and go 7 to the right, we're at 7 on the number line. Now, one very important thing that we've got to do in algebra is this algebraic habit of mind that we need to get into, that we need to think of things as doing them and undoing them. And any process that we study, we're going to want to be able to reverse it by applying the inverse process. So what is the process that's the inverse of addition? What will undo addition? What is addition backwards? Well, you know this. It's subtraction. The inverse operation of addition is called subtraction. So subtraction reverses addition. If we start with a number a and add b to it, and then we turn around and subtract b from that sum, then the two operations cancel each other out, and we're back at the original value that we started with. So a plus b first, then subtract b, you're back at a. Subtraction models a takeaway situation. So a simple real-world example is, you have 6 apples, and Sam takes away 2 apples. How many apples are left? And there are 6 minus 2 equals 4 apples left. Subtraction solves a missing sum-in problem, or missing add-in problem. So we want to solve for a. A plus 5 equals 11, or 5 plus a equals 11. So in other words, you're saying, okay, what do I start with and then add 5 to get 11? Or if I start with 5, how much do I add to it to get 11? And the answer is 11 minus 5, which is 6. So addition and subtraction form a fact family. So the following relationship is the same relationship among the quantities a, b, and c. So in other words, if you say a plus b equals c, that's the same thing as saying c minus a equals b, or c minus b equals a. In fact, c minus a equals b is defined by a plus b equals c. So 3 plus 4 equals 7 is the same thing as saying 7 minus 3 equals 4, or 7 minus 4 equals 3. These are the same relationship among 3, 4, and 7. So on the right we have arithmetic, on the left we have algebra. Now another algebraic property we want to talk about is called closure. So notice that when we add any two natural numbers, the sum is always a natural number. And that also works for whole numbers. You take any two whole numbers, the sum is always a whole number. So in general, if we can perform an operation on any two elements of some set of numbers and the result is always back in the original set of numbers, we say that that set is closed under that operation. So the set of natural numbers is closed under addition, and the set of whole numbers is closed under addition. Symbolically, we can write it this way, and we read it like this. If A is an element of the set of natural numbers and B is an element of the set of natural numbers, then A plus B is an element of the set of natural numbers. If A is an element of the set of whole numbers and B is an element of the set of whole numbers, then A plus B is an element of the set of whole numbers. So here's a question for you. Is the set of whole numbers closed under subtraction? Press pause and think about that a second and then come back with your answer. Okay, well now that you're back, to answer this question, if the answer is no, we have to find an example of two numbers that we subtract and it's not, two whole numbers we subtract that's not a whole number. If it's true, then we would say it is true no matter which two numbers we subtract, we get which two whole numbers we subtract, we still get a whole number. Well, which is it? Well, let's take a look at it. If we can, sometimes we can subtract, okay? So we can do 6 minus 2, and we get a 4. 8 minus 8 is 0. 15 minus 3 is 12. Those where we started with two whole numbers, and we got a whole number back. But there are some subtractions that cannot be performed in the set of whole numbers. So if A is 2 minus 4, then what we're saying is 4 plus A is 2. We're saying start at 4 on the number line. How far do we go to the right to get to 2? And the answer is it can't be done. Okay? Because when we're adding a whole number, we're always going to the right on the number line. Okay? Notice that 4 plus A is always greater than or equal to 4, which is greater than 2 for any whole number A. So A, which is 2 minus 4, is not an element of whole numbers. Other examples would be 0 minus 1, 8 minus 11, 16 minus 25. They're not elements of the set of whole numbers. And similarly, the set of natural numbers, neither the set of natural numbers nor the set of whole numbers are closed under subtraction. So if we want to undo multiplication, no, that should say addition. We want to undo addition, that is, solve missing add-in problems. That should say add-in, that should say addition. In other words, we want to perform subtraction, then we must expand our number system. The whole numbers are not going to cut it. So if we want to expand our number system so the new system is closed under subtraction, but we want to do this in such a way that this expansion is consistent with the concepts we've already developed of natural number concepts of addition and subtraction, and we want to retain these important properties and patterns. So we want to keep as much as we can of this idea of a blocks model or a number line model. So what are we going to do? Well, we go to a bigger number system called the integers. Now, if we have the idea of a identity, which is 0, then we can talk about the idea of an inverse. So an additive inverse is a number that we can add to A and get the identity element, in other words 0. And it shouldn't matter which order we do it. So we're going to denote this additive inverse as the opposite of A, with this dash and an A. So the opposite of A plus A is the same as A plus the opposite of A, and that is 0. So the additive inverses of the natural numbers are not natural numbers themselves, and we call the additive inverses of the natural numbers the set of negative integers. And we throw those in with the whole numbers, and we have the set of integers. So we use a blackboard boldface Z to denote the integers because the German word for integers is Zahlen. The Germans get to name one of these symbols. Okay, there goes with their word. So here is the set of integers. Not only is it 1, 2, 3, 4, 5, 6, 7, 8 forever, and 0, it's also negative 1, negative 2, negative 3, negative 4, negative 5 forever. So when we put this on a number line, it's still evenly spaced dots in a line, but now it goes not only to the right forever, but also to the left forever. Okay? And so that's the set of integers. Now, we have an idea of greater than and less than. If a number A is to the left of B on this number line, then we say A is less than B, and we write it this way. If A is to the right of B on the number line, we say A is greater than B, and we write A is greater than B in this symbolic way. So now we're going to define what we mean by positive, negative, and 0. So in general, a real number, as we get to later, that's less than 0 is called a negative number, and any number that's greater than 0 is called a positive number. Now notice that 0 is neither positive nor negative, and all the natural numbers are positive and all their additive inverses are negative. The inverses, additive inverses, come in pairs. So negative 4 and 4 are additive inverses of each other. 4 is the inverse of negative 4. Negative 4 is the inverse of 4, the additive inverse. So the opposite of negative 3, or the additive inverse of negative 3, is positive 3. The additive inverse of positive 3 is negative 3. So you can think of this as the two negative signs canceling each other out. Alright, how about some more exercises? What symbol is used for the set of integers? Why is this letter used? And so forth. I'll let you read these questions and come up with your own answers. After you do those, come back and we'll check them here in just a minute. Press pause now. Okay, we're back. Let's see how you did on these examples. The symbol for the integers is this funky looking Z here. Why is this letter used? It's the first letter of the word Zahlen, which is the German word for integers. List the set of integers. Here they are. We've listed enough to hopefully see the pattern, but notice it does go forever left and forever right. Use subset notation to indicate the relationship among the three sets of numbers. So this says the set of natural numbers is a subset of the set of whole numbers, which in turn is a subset of the integers. So all whole numbers are integers, but there's some integers that are not whole numbers. All natural numbers are both whole numbers and integers, but there's one whole number that's not a natural number, 0, and there's a lot of integers that are neither whole numbers nor natural numbers, all the negative ones. So from a mathematical completeness perspective, why are the integers necessary? If we want to be able to subtract natural numbers, solve missing add-in problems, and reverse addition, we need the integers. Give some real-world examples where integers are necessary. Well, we can use a positive to indicate an increase and negative for a decrease. Temperatures. If you have a metric system scale, okay, then 0 degrees Celsius is freezing of water. Temperatures that are warmer than that are positive. Temperatures that are colder than that are negative. Gain and loss. Gain could be positive, loss negative. Surplus, deficit. Surplus is positive, deficit is negative. If you have a debt, you might represent that as a negative number. Lots of other uses as well. So integers have nice real-world physical uses as well. In fact, the symbol, positive and negative symbols that we use sometimes for the plus and minus symbols, were first used, as far as we know, in Europe whenever they had barrels and they were measuring what was in the barrels. If the barrels were overweight or over volume, they'd put a plus by how much. And if they were under, they'd put a minus by how much. And that notation eventually got caught on for using that. Now notice that, some cultures like the ancient Greeks, the idea of a negative number didn't even make sense to them because they thought of everything as a length. See, lengths have to be 0 or positive. They can't be negative. Okay? So a negative number just wasn't even in their realm of possibilities. Okay? But we do see that there are lots of real-world physical things that we can use negative numbers for. So which of the following sets of the numbers that we mentioned so far, are closed under addition? Well, they all are. The natural numbers, whole numbers, and integers are all closed under addition. In other words, if you start with two natural numbers and add, you get a natural number. You start with two whole numbers and add, you get a whole number. You start with two integers and add, you get an integer. Which of the sets of numbers mentioned thus far are closed under subtraction? Well, only the set of integers is closed under subtraction, the ones we've talked about. If you subtract two integers, you do get an integer. But the natural numbers and whole numbers, we've seen that there are examples where you could subtract two natural numbers and not get a natural number. And same for the whole numbers. So they're not closed, but the set of integers is closed. Is subtraction commutative? Well, no, it's not commutative. In fact, it's almost never true. If you take a minus b, what is true, it's the opposite of b minus a. So a minus b and b minus a are almost never equal to each other. In fact, the only way they can be equal is if they get, a minus b is the opposite of b minus a, so you'd have to have a number which is its own opposite. Well, the only number that it's its own opposite, its own additive inverse, is 0. So the only way a minus b could be equal to b minus a is if a minus b equals 0, which means a equals b. See, the only way that you're going to get a minus b to be b minus a is if a and b are the same number. Otherwise, a minus b is the opposite of b minus a, not commutative. So we can think of integer addition and subtraction we're going to actually define subtraction as the addition of the additive inverse. So we're going to define a minus b, this colon equals means defined to be equal to. A minus b is defined to be equal to a plus the additive inverse of b. So 3 minus 4 is defined to be 3 plus a negative 4. 6 minus a negative 2 is defined to be 6 plus the opposite of negative 2, which is 6 plus positive 2. Negative 2 minus 5 is defined to be negative 2 plus negative 5. So now you're going to think of subtraction really as being addition, but addition of the additive inverse, the opposite. Now if you're adding a positive number, you're going to the right. If you're adding a negative number, you're going to the left on our number line. So, for example, 9 minus 5 can be thought of as 9 plus a negative 5. So here we have 9, which is the blue, going to the right from starting at the origin, go to the right 9, and you're at the point 9. And from there, we want to add negative 5, that is, go 5 to the left. So the green one is 5. That's what we have here. But then its opposite is 5 going to the left. Now move that red one to the end here. So in other words, we start at the origin, we go 9 to the right, and then we go back to the left 5. And where do we end up? We end up at 4. So the purple going to the right 4 is the result. So we can do number line problems like this. Here's some other examples. Negative 1 minus 5 says we start by going left 1 and then left 5 more to end up at negative 6. Negative 2 minus a negative 4 is, say, negative 2 plus 4, okay, which means we go left 2 and then right 4, and we end up at positive 2. Negative 5 minus a negative 4 is negative 5 plus, positive 5 minus negative 4 is positive 5 plus 4, means we go the right 5 and then the right 4 more, and we end up at 9. So, the set of integers extends the set of natural numbers in a way that is consistent with the meaning and properties of the natural numbers. The set of integers is closed under addition and subtraction. Any missing, I'd rather use the word add-in problem, can be solved in the set of integers. So a plus 3 equals 1 can be solved for a. A is negative 2. The set of integers is absolutely required if we want to solve any such missing add-in problem involving given natural numbers. In other words, the set of integers is required if we want to be able to undo addition. In other words, perform subtraction. Now here's some review of some properties that the integers have. And notice most of these are the same properties that we had for natural numbers. And that by the way we've done this, we've extended the properties of natural numbers first to the whole numbers, then all the way to the integers, in such a way that these properties will keep going. The integers have additive closure. A plus b is always an integer for any integer a and b. The associative property of addition says if you take a plus b and add it first and then add c to it, it's the same as taking b plus c first and adding that to a. Additive identity is 0. So if we take a plus 0, that equals 0 plus a, which is also back to a again for any integer a. Additive inverses. For any integer a, there exists an additive inverse, negative a, or the opposite of a, in the integers, so that the opposite of a plus a equals a plus the opposite of a, which is the additive identity 0. So subtraction is defined as adding the additive inverse. A minus b is defined to be a plus the opposite of b. And with the commutative property of addition holds, a plus b equals b plus a, but not commutative for subtraction. Absolute value we can think of physically as a distance a number is from 0 on number line. And algebraically, the absolute value, sometimes written as abs of x, or these two vertical lines, it's defined to be x if x is greater than or equal to 0, and the opposite of x if x is less than 0. Now notice this minus x down here is actually a positive number because the x in this bottom case is a negative number. So the absolute value of negative 3 is the opposite of negative 3, which is positive 3. But the absolute value of positive 3 is 3. So this is an example of what we call a piecewise defined function. We'll talk more about later. But here's what's happening here is we have our input, and if our input's positive or 0, the output is the same. Nothing happens to it. But if the input is a negative number, we say, okay, we're going to do a little operation on you here. We're going to change your sign or remove your negative sign. So notice that both negative 3 and 3 are 3 units from 0 on the number line. So let's do these some basic exercises here as well, and let's finish up this particular video. So go ahead and do this. Press pause now. Okay, now we're back. Let's see if we can work through these. So subtraction is defined as adding the additive inverse. So by definition, a minus b is a plus the opposite of b. So some simple rules for subtraction of integers is this. Rewrite the subtraction as adding the inverse. Now then you want to add integers. If the two add-ins have the same sign, that should say, add their sizes, their absolute values, and keep the same sign. Size, it should be sign. If the two add-ins have opposite signs, then subtract the absolute value of basically the larger one minus the smaller one, as far as their absolute values go, and keep the sign of the one that has the larger absolute value. So, for example, 3 minus 7 is 3 plus negative 7, so 7 is bigger than 3. Take 7, take away 3, 4 is left, but we use the sign of the negative 7. Or think of it as going to start at 3 on the number line, going 7 to the left, you end up at negative 4. Negative 2 plus 8 is 6. Negative 3 plus negative 5 is negative 8. So you just add the 3 and 5 to get 8. Keep the same sign. Negative 4 minus 6 is negative 4 plus negative 6. So again, 6 plus 4 is 10, but keep the sign as negative. 8 minus a negative 2 is the same as 8 plus 2. Negative 8 plus 2, which is negative 6. Negative 6 minus 5 is 1. 8 minus a negative 7 is 8 plus 7, which is 15. So that's going to complete this particular video. In the second part, we're going to go on and talk about how we can derive the idea of multiplication, the distributive property, how we reverse it to get division, and how that's going to lead us to the set of rational numbers.